Hello everyone. Today it is my honor to introduce you the program that is meant to bring all the disciplines together. Data-centric systems engineering is a transdisciplinary approach required for the development of large, complex, and reliable systems, whether these are products, services, or enterprises. It provides a structured development process that evolves from concept through production to operation and to delivery. It is a top-down approach, and the program places a strong emphasis not only on data analytics and technical contents in our modules, but also on cross-disciplinary skills vital for an engineer to be effective in the workplace and within the systems engineering field. My name is Chen, and I am the program lead on this MSA program in data-centric systems engineering. My research interest includes operational research, machine learning, and their applications to intelligent transportation systems. I'm going to teach you statistical thinking and machine learning and engineering design optimization modules on this program. We also have a mix of excellent academics with different expertise in systems engineering. Here I provide a small sample of member of staff on the team to deliver this program. Obviously, we have many other staff with different expertise who are also going to contribute to this program. We have Professor Vasily Toropov with interest in multidisciplinary design optimization, multi-modeling, and structural optimization. We have Mohammad Hassannezhad with interest in socio-technical system design, system of systems engineering, resilience engineering, human in the loop, decision making. We have Yunpeng Zhu with interest in data-driven dynamic systems, complex system analysis and design, vibration and control, and system condition monitoring. We have Michael Weiser with interest in optimization, meta-heuristics, simulation, IOP Operations, and multimodal transport. We have Xinwei Wang with interest in decision-making, risk assessment, machine learning, intelligent vehicles, and aerospace engineering. Together with other members, we are going to deliver a range of modules for this program. The program consists of 5 compulsory modules and 2 elective modules, and an extended research project over 1 year. These modules provide a guide to the characteristics of systems and fundamental principles of systems engineering. They provide techniques and tools to acquire and process digital data, and for modeling complex real-world engineering systems. They also provide mathematical models, numerical optimization algorithms, and complex decision analysis methods for a wide range of engineering system and product design problems. You will learn how to use statistical and machine learning tools to derive insights from data and automate routine engineering tasks. The program will introduce several dimensions of ethical design considering the system life cycle, including the impact of end of life, as well as the hazards encountered in industry process plants and how to prevent loss. By the end of the program, you will gain sufficient knowledge in order to become an associate systems engineering professionals within the in-course certification program, and have the necessary capability to work towards the certified systems engineering professional. The School of Engineering and Materials Science at Queen Mary University of London is one of the best places for you to learn systems engineering and become specialized in one of the research areas within the school through coursework and case studies in each module and the extended research project. The school are also hosting research excellence networks and centers, providing lots of opportunities and facilities for you to get involved in internationally leading research with industry partners at a top UK university. In partnership with New College London, Queen Mary also hosts the London City Institute of Technology. We work closely with anchor employers of the Institute and other industry partners to help continuously develop our curriculum offer. At this point, I think the best way to demonstrate data-centric systems engineering is through examples. The first example that I'm going to give is for future airport operations, which is going to be more digitalized, automated, efficient, and environmentally friendly. In not a distant future, pilots are going to receive instructions, including which taxiway to take and at which speed, from more intelligent decision support tools. These instructions will enable more precise control of aircraft movements, so that it not only avoids conflicts with other aircraft, but also represents the best way to taxi at that particular moment. This problem is a perfect example of how different disciplines and components at different levels need to join together in order to address concerns from different stakeholders. It integrates flight dynamics, control engineering, computer science, navigation and guidance systems, and human-machine interaction to achieve improved punctuality and reduced fuel burn and emissions. It requires a systems approach to analyze and define stakeholders' requirements, optimize to obtain trade-off solutions, explore trade space, design novel onboard display systems to inform pilots and air traffic controllers, and integrate them in the new operational scenarios. Lots of similar examples exist in applications ranging from transportation, robotics, sustainable energy generation and storage, finding new and better materials to healthcare. We provide training for future system architects and project leaders in these fields. Next, I'm going to hand over to my colleague Mohammad to give you more examples and also the career path after taking this program.
In this second example, I will introduce the application of systems engineering to the design of complex materials. The University of Bristol developed a special foam which can be used to absorb vibrations in hi-fi audio systems and wheelchair mats for disabled people. Current design and manufacturing of complex foam materials are often conducted based on many runs of experiments or computer simulations. However, these approaches are often time-consuming. The challenge is how to produce a high-fidelity, reduce-order model and conduct a model-based design for engineering materials and structures withstand demanding dynamic loads. To address this problem, a novel approach was developed that combines system science methodologies with data-driven modeling. The basic idea is to find a simple model of a foam from data, which is obtained by only doing few experiments or simulations. After that, the simulation model can be used to conduct fast analysis and design for the foam material. To support the implementation, a MATLAB toolbox was developed for industrial applications, which can be used to automatically generate material design from the foam. The approach can significantly reduce the time for material design and manufacturing, with the potential to discover material dynamic properties from the data-driven model. From the examples, we can see that systems engineering is not just about developing new technologies, but also about understanding how different bits of technologies should stand together to achieve the expected performance outcomes. For example, with the automotive sector, if we go back to 1950s, it was a purely mechanical component with minimal interfaces, but nowadays it's quite difficult to say whether it's a computer or a piece of software technology that is covered by some mechanical components. Systems engineering help us to understand the best trade-off between functionality of developing new technologies on the one hand and the emerging complexity and cost of the end system on the other hand. Similarly, in the context of fighter jets, we can see such a growing complexity of the system in terms of the number of interfaces, where the portion of software codes had almost been quadrupled in the past few decades. In this program, we are using a mix of methods, tools, and techniques for better learning experience by bringing a variety of examples from engineering systems into the lectures, running detailed investigation of case studies, such as the Columbia Space Shuttle disaster, to learn from systems engineering failures, running workshops and design competitions, as well as facilitating the network and communication between the students. Regardless of your background in mechanical engineering, electrical engineering, chemical engineering, or aerospace engineering, our approach will hopefully enable you to obtain a good blend of technical and management skills, mainly those which will be required when working in industry. Our program is completely aligned with the standards provided by the International Council on Systems Engineering. So, supported by a range of SEMS facilities and resources already mentioned, and regardless of your background, you will have the opportunity to shape your future career towards becoming an associate systems engineering professional within COSI immediately after the program, and eventually certified systems engineering professional after 5 years of getting experience in the field. If you have any question about the program, its requirements and formats, please get in touch with the SEMS School Office or the Program Director, Dr. Chen. Thank you for listening to us and looking forward to welcoming you in Queen Mary.